Ladies and gentlemen, welcome to this second last lecture for the short course of base isolation systems and generally seismic isolation. So we will see some very fast rules to be implemented within the Matlab environment in order to fully characterize the theoretic response of isolation devices. We will see together that actually there are some simplifications, but what we will come up with will be theoretic rules and functions that we can adopt also for nonlinear time history analysis. Obviously, for simplified systems like lumped masses or oscillators. In this lecture, we will consider just a single degree of freedom oscillator, but generally I can say that in my practice, I used to consider these such procedures also for multi-degree of freedom oscillators. So even if you account for a number of degrees of freedom for also the stories of the building, and you can do it by modeling elastically, I mean, all the floors. And then you can add the nonlinear theoretic rule for the isolation system. Just some information about the organization. Tomorrow there will be the last lecture where we actually we will be comparing the results that we are going to obtain today to actually the results that we got yesterday. Obviously, they will be completed simply because there was no time for us to actually run all the analysis. But then at the end, we will do some comparisons. We will draw some concluding remarks for what we have seen. There will be for sure some time, sometimes for questions and to answer some doubts. And then today, I think within today afternoon, I would like to provide you with a very simple homework to solve. It is very simple. It will be about what we have seen for fast design of isolation systems, for what we have seen together. It will be exactly the same procedure that we have adopted in our case study, but just applied to a different case. So I think that you could be able to send me the overall results on next Tuesday. The Tuesdays of next week, and then I will see the overall results that you will get. I will send you this particular homework through the email within today afternoon. So is there any question about what we have seen yesterday? It was a very long numerical laboratory, and we have seen a lot of issues about the finite element model for both the superstructure, the characteristics of the superstructure, and especially for the behavior of isolation devices. Is there any doubt about that? Or generally any information required for any topic that we have covered? Okay, so I think we are able to start. We will see a little bit of a theory at the beginning, and actually we will start from what we have already done, as you may remember on Tuesday or last Tuesday, about the time integration of the single degree of freedom oscillator, the linear elastic one, when we had actually to build up the response spectrum for a given accelerogram, so for a given ground motion time series. Actually, we have just jumped up into the equations without any reasoning. So what I want you to see is also how the equations that we have used are derived, and then obviously we will try to generalize them in order to apply the same time integration method also with the different hysteresis loop that we are going to use also for different devices. So I start by sharing my screen. And then we can start actually by considering some theory. but that will be very fast. I mean, not too much. Just a brief overview of what we are going to analyze. So as I mentioned, today we will just consider a single degree of freedom oscillator, which can be actually a fairly good representation of what happens for seismically isolated systems. We have discussed at the very beginning of this short course that the overall structure, for instance, a building which is base isolated through particular devices, can be directly associated to a single degree of freedom, just because, if you remember, we associated the overall system to a series of two springs. We neglected approximately the mass of the plate, which is the interface between the superstructure and the isolation system, so that we were able to compute the expression for the equivalent stiffness of the series of the two springs. And then by considering the stiffness of the building, which is much higher with respect to the stiffness of the isolation layer, since we are going to provide the proper period shift, we can have actually the overall system simplified as a single degree of freedom oscillator, where the mass is actually the total mass, which is above the isolation devices. And the stiffness can be represented by the stiffness itself of the isolation system. We have to pay attention on these terms. I mean, okay, the mass is the mass of everything, which is above the isolators. But we have, as you now know from this course, we have to pay attention on the word stiffness, because the stiffness is generally associated to something linear elastic. And for what we have seen, our isolation systems are highly nonlinear, especially for lead rubber bearings and curved surface sliders. Also for rubber bearings, I mean, there is a little bit of hysteresis, which can be modeled through a linear dashpot. Okay, there will be a very small hysteresis. This is why they are directly associated to very low values of damping ratios. But then we know, as we have seen yesterday also in SAP 2000, that we have also to model the hysteretic response of frictional devices, and that is actually highly nonlinear. So let's start from the very first assumption, which is actually the single degree of freedom oscillator. So we have actually these static scheme. We will have the total mass, and let's call it small m, which is better. And then, okay, I would like to say that we don't have a linear elastic one, but generally we will have a force response for this single degree of freedom oscillator. And let's call it, since we are going to model actually seismically isolated systems, let's call it F isolation. Okay, so if we have actually a linear elastic oscillator, that F isolation that will be equal to K times the displacement, so the stiffness times the displacement, plus the damping coefficient C times the velocity. Both displacement and velocities, obviously, as you know, are relative quantities. And generally, when I say this, is just because we consider this reference system where we have the displaced single degree of freedom, and this is X ground. So the displacement of the ground, and then we have the relative displacement. And we have also the absolute displacement with respect to the position of the mass and the fixed reference system. Okay, and the same, okay, we have so that the absolute displacement is equal to the ground displacement plus the relative displacement. And the same equation can be also considered for also the derivatives, the time derivatives of all the quantities. So the absolute velocity is equal to the velocity of the ground plus the relative velocity. And actually, the let's consider this one, the the double derivative of with respect to time. So we have the absolute acceleration equal to the acceleration of the ground, so the accelerogram, plus the relative acceleration. Okay, so this is very important simply because this allows us to consider also the second dynamic law, which considers the summation of all the external forces equal to m times the absolute acceleration. Okay, so the only, the only external force which is applied is actually the one. This is okay in this way, associated to the elastic. When we consider an elastic oscillator, we consider just k times the displacement. Otherwise, we consider the generally F isolation when we want to consider any kind of generally device. And if this is the force, the shear force applied to actually the body, let's say, of the oscillator, there will be an opposite direction also to the mass, applied to the mass. So we will have actually m, which multiplies the expression of the absolute acceleration, which is xg ground motion plus the relative the relative acceleration equal to minus F isolation. So this is simply because if we consider the equilibrium, the translational equilibrium of the mass, we have to change direction with respect to the forces that I've just drawn. So the final equation will be m relative acceleration plus F isolation equal to minus m accelerogram. Okay, so this is the main equation of motion that we will consider. Okay, so let's start from the we will start now from the general theory for time integration. As I mentioned on Tuesday, we just apply an explicit time integration method, which is actually the least accurate that you can choose because it is not iterative. There is just the solution is just given at the first computation at each time step, and it is actually explicit. So it is not so much accurate, but the accuracy of time integration methods directly depends on the size of the time step. If this time step is significantly low, like actually the ones that we consider, I think that 0.01 seconds is actually enough to properly define the overall response. We can actually use this this method because the final results are quite good in comparison to other methods. So let's start by considering this method. So we will start again by looking at the differential equations of motion. So m times relative acceleration plus F isolation equal to the mass times the ground motion in terms of accelerogram. So what we want to analyze now is the same equation, but by considering at the very first member of the equation the relative acceleration, just the relative acceleration equal to something. So we want to consider this like this expression. So second derivative of relative displacement, so relative acceleration equal to, so we have to move everything in the second member of the equation. So we will have 1 over the mass times minus mxg ground motion, so the acceleration, minus F isolation. Okay. So why have I done this? Just because now we can switch to, instead of having these actually the second derivative of the relative displacement, which is the relative acceleration, we want to consider that at the end we have to compute some integration methods through actually discrete signals. This is the definition of the motion, but just in a continuous theory. Then we have to consider that the accelerogram is given as a discrete signal. So let's assume that this quantity, which is the relative acceleration, generally is assumed as the derivative, the first derivative of the relative velocity with respect to time. Okay, but if we go through the discrete theory, we switch from a ratio of differentials to just a variation quotient. So we can say that, okay, there is already the arrow. We can say the relative acceleration is equal to the variation of relative velocity divided by the variation of time. So these are not differentials, but they are actually variations. So depending on the variation of time, the time step according to which the accelerogram is sampled, we will have obviously a variation, a corresponding variation also with respect to the relative velocity. So this is useful because this can be also written as follows. Okay, here we have delta t. We know that signals are generally returned with constant sampling frequency. We have seen the sampling frequency in the first numerical laboratory related to the recorded signals during dynamic tests. But the same is applied also for accelerograms because accelerograms are just recorded signals of ground accelerations through accelerometers. So you have also the definition of sampling frequency also within the accelerogram. And also in that case, accelerograms are sampled through a constant value of sampling frequency, and so automatically we have the time step which is constant along the whole direction, the duration of the signal. And the variation of the relative velocity is equal to relative velocity at the ith time step minus the relative velocity at the ith minus 1. Okay. We can say this rather than the first velocity is correspondent to the ith plus 1 and the second to the ith. Okay, the definition is the meaning, I mean, is always the same. So if we use this expression, which is the discrete one, the differential, the variation quotient, let's consider it here according to this expression. So we want to switch from this definition, which is continuous, to a discrete one. And so we will get the variation of velocity divided by delta t equal to 1 over m, which multiplies minus m xg second derivative minus isolation force. And so finally, we get the expression that we used on Tuesday. So the ith relative velocity is equal to the ith minus 1 relative velocity. Okay, plus variation of time divided by the mass, which multiplies. Okay, now also here in this second member of the equation, we have to switch from the continuous theory to the discrete theory. So instead of having generally the accelerogram, we should also highlight that this is just a fixed value for a given time instant. So we can fix it to the ith time instant, simply because generally, what is the according to this definition, what is at the ith time instant is unknown for us. Okay, everything but the accelerogram, because the accelerogram is a given signal at the beginning, so it is entirely known. Okay, so this is not what happens for the for isolation force, which is okay, relative to the I minus 1. Okay, so this is why it is called the explicit method, just because everything in the second member, which is unknown, is explicitly associated to the previous time step. So it is a strategy for us to consider something which is unknown as known, because we already know something which has already happened. So in the previous time step. And also at the beginning, we know it, because generally we start from the initial conditions, which are given for us will be 0, because generally when the earthquake comes and occurs, we don't have any displacement and any velocity approximately, let's say. So we will start from 0 initial conditions. And so here we have minus m accelerogram at the ith time step minus force of isolation system at the ith minus 1. Okay, so this is actually the first equation to obtain the time integration, and then this is just to obtain the relative velocity at the ith time step. So how to compute the displacement? The displacement is actually this the solution of our problem, of our differential equation of motion. And to do this, we will use exactly the same definition that we used here, but we will use it not for the relative acceleration, but we will use it for the relative acceleration. Sorry, for the relative velocity. So we have relative velocity generally equal to the first derivative of displacement with respect to time, and if we consider the discrete time axis, we get that the relative velocity can be obtained as the variation of displacement with respect to over the displacement, the variation of time. So according to this, we can say that the displacement at the ith time step is equal to the displacement at the ith minus 1 plus variation of time times the velocity, the relative velocity at the ith, which has been already computed here. Okay, so these are the equations that we need to time integrate the single degree of freedom oscillator. So now what we have to consider is actually the definition of the isolation force. Okay, so we will have to consider the different behaviors that we have, and then to combine them. Maybe if we have hybrid systems, we can actually try to combine flat sliders together with linear elastic oscillators for rubber bearings, rather than elastoplastic with hardening for lead rubber bearings. Any questions from this? Okay. So finally, let's check all the hysteretic rules for all the devices that we considered. So let's start from the easiest. So rubber bearings. Okay. So we know that the overall behavior of rubber bearings can be modeled through a linear elastic, I mean both stiffness and spring with both stiffness and damping factor. So this means that we have actually a spring and a dashpot. Okay. Something like the Voigt model. And we have generally K and C. So for us, the F isolation will be equal to K times the displacement plus C times the velocity, so the relative ones. So relative displacement and relative velocity. And that's it. This is very easy. This is actually also the equation that we have seen on Tuesday to build up the response spectrum. Obviously, we have 5% of damping ratio because, as you remember, the spectrum compatibility of the selection for ground motions should be checked and evaluated by considering 5% damping ratio for all the response spectra for both the target one and all the spectra coming from the single events. Okay, here we will have actually the C value, which is returned by the, directly by the typology of the rubber compound, and we have seen different damping ratios related to different compounds, medium, soft, and hard compounds. So we have seen how to define both the key value and also the C value. For rubber bearings, we will have generally a number of isolation devices. So we will have just an isolation, which is the number of isolation devices for us. And then if we want just to try to model them, just rubber bearings with no flat sliders, we can set the K equal to number of isolation devices times the stiffness of the single device. And you remember that it is equal to the shear modulus times the horizontal cross-section area divided by H isolation. Okay, so this will be the total stiffness associated to rubber bearings, whereas the damping coefficient C is equal to twice C, which is damping ratio, omega isolation, and let's say the mass, the total mass of the oscillator. So, the omega isolation can be obtained by considering the design period. So we will have 2 pi over T isolation. Okay, so you see that I don't have to multiply these by the number of isolation devices because this expression is already the definition of the global damping coefficient. And actually, it is the opposite. Yesterday, when we had to compute the damping coefficient for the isolation devices, the rubber bearings in SAP 2000, we had to divide that number by the number of isolation of isolators in order to compute the real number. This is already the final number that we have. So now there is my cat, which tries to ask questions. So I think that this is done for rubber bearings, but what we want to also to consider are flat sliders, because generally we have also the hybrid system, so the combination of both flat sliders and rubber bearings. So instead of switching to lead rubber bearings, I would like to start with the frictional behavior. Then we will see the response for curved surface sliders and so on. So let's start from generally the friction isolator. Okay, So according to frictional isolators, let's consider both the curved surface sliders and also the flat sliders. So this means that we will have just, we will start from the frictional response, and then we will have also the opportunity to add a linear recentering behavior, which is just a linear string with respect to displacement. So we know that the theoretic response is something like this for frictional behavior. So let's consider the relative displacement and the force. Let's say isolation. If this is just purely frictional response, we have something which has a rectangular shape. Okay. And how to model this? Okay, in SAP 2000, we have seen that also for flat sliders, generally curved surface sliders, the overall rigid plastic behavior for friction can be associated to actually an elastoplastic equivalent behavior. So we have to define an initial stiffness, which is quite high, which is representative of the behavior of friction, and then obviously it is not a straight line, but it is inclined. But if the initial stiffness is reasonably high, we can actually model, obtain the overall response in the best way that we can. And this is an opportunity. So there is another very simple equation that we will see also the modeling assumptions for the elastoplastic behaviors. We will do that. But first of all, I want to show these. Generally, the Coulomb friction is returned by this equation. If you check in the scientific literature, you can check that the, let's say again, F isolation in terms of pure friction. This is equal to friction coefficient times the weight of what is above the device times the sign of the relative velocity. Okay, this is what is generally assumed for the Coulomb friction, and this is actually a modeling strategy which returns that shape of hysteresis loop. So this is very useful. This can be used actually to time integrate the overall behavior of the single degree of freedom oscillator. But what we get is something like this, but a little bit different. I mean, if you check these, what we get is something like this. So what we start from 0. Okay, there is displacement and force, isolation. We start from 0, and then we don't have any transition from 0 and the maximum force, which is the frictional force, but we have immediately the frictional force, and then it constantly remain the same number. And then if we unload the overall device, generally the oscillator, we switch from here to here. Okay, and then we have these, and then we switch from here to here. Okay, so what is missing is actually the set of points for the unloading branches and the loading ones. Okay, so this is so yeah, I can also try to show these through the Excel. So just to see, let's check our maximum displacement. Let's assume this quantity, a friction coefficient equal to 5%. vertical load in kilonewtons. Let's consider the whole weight of the structural system. So yesterday we had the 1,300 tons, which means approximately 13,000 kilonewtons. And then I think that we are done. So the frequency, okay, if we want to simulate, actually to numerically simulate an experimental test, let's assume the frequency as 0.5 Hertz. Okay, so we will have time, and we want to sample time according to actually 1/256 Hertz as a sampling frequency. And then we have to go, we want to consider a full cycle. So what we need is actually to go up to 1 over the frequency. So actually 1 over 0.5, which is 2. 2 is the duration of the whole cycle. So let's just copy the this expression in order to the previous one plus. Okay. Okay, we have a lot of points. We need, you see, now we are at 2. This is 2. Okay. Okay. So this is a full cycle. Then we want to also draw the displacement. So this is what I call the U of t in terms of meters. And this is d max times sinus of 2 times pi times frequency times time. Okay. Okay. So if we want to check if the signal is right, okay, this is a full cycle, and you see this is the displacement times signal, which could be actually the input for the testing equipment to carry out a dynamic test. So according to this signal, we want to obtain, to simulate actually the hysteretic response for just pure friction, okay, according to these quantities. So first of all, we need the definition of the velocities. So let's say U dot, which is a first derivative in terms of meter per seconds. Okay. And okay, we start from 0 because this is an initial condition for our problem. And then we have just to apply the differential quotient. So equal to the variation of displacement divided by the variation of time. Okay. I don't know if at the end there is again the drawing. No. Okay. So let's draw it again. If you remember when we did this in the numerical laboratory, there was the actually something which looked wrong, but actually it was not. If we just check the velocity like this, okay, you see the first derivative of a sinus is a cosinus. So you see here the shape, this is exactly a cosinus, but we start from 0. Okay, because generally now we are just simulating the effect of, I mean, the input signal, but then we will have to time integrate the overall ground motion. So there will not be any gap in our final integration. This is not actually an integration, but this is just a numerical simulation. So what we can do is to consider maybe the maximum velocity value according to this. So the maximum in meter per second, just to be consistent, is equal to 2 times pi times frequency times maximum displacement. Okay, and we can start from that value. Okay, so now everything is more correct, let's say. And we will not have to do that when we will be integrating the ground motion, because we will surely start from zero velocity, because everything is in equilibrium and there is no motion before the earthquakes occurs. Okay. So now let's start. We want to simulate the frictional response. So F isolation in terms of kilonewtons. So let's try to apply the what we have seen here. So the Coulomb definition for the frictional response. Okay, so we have just coefficient of friction times structural weight times the sign, which is segno in Italian, of velocity. So the every value along this column. Okay. And that's it. So what we want to consider now is the displacement with respect to the frictional force. Okay. So you see that this is actually a rectangular hysteretic rule. This looks like a purely frictional force, but if we just change the typology of of a graph, and we want just to see also not only the lines, but all the connecting lines, but also markers. So like these ones, you see that we have markers just along these horizontal branches, so along the frictional forces, and we don't have any marker here for the unloading and neither for the loading branches. This is not actually what happens in reality, because actually these are values of forces which are experienced by the structural system. So there is this information which is missing in these computations. So in order to better characterize this, I go back to the slides because I have to show you what I mean. So according to this definition, we can have actually the frictional force with respect to the velocity. Okay, if we consider the sign, so the Coulomb's theory, we have just this. This is the graphical representation of the sign function. Okay, we have a gap at zero velocity. Okay, and this is the reason why when we have zero velocity, which is actually when we achieve a maximum and minimum displacement, we don't have any values inside this transition branch. Okay, so this is the Coulomb's theory. What we generally assume for this behavior when we don't want to consider an elastoplastic behavior, but we are going also to consider this, is something similar. So something which provides actually also the transition values from the minimum to the maximum value of the frictional force. So something like this, okay? Something which is continuous, there is no gap. And actually, okay, here everything is graphically stressed, let's say, in order for you to see the transition. But our goal is actually to define this transition as much vertical as we can, simply because we have to model the frictional behavior, which is a rigid plastic behavior. So according to this equation is F isolation equal to coefficient of friction times the structural weight times the hyperbolic tangent of the velocity divided by a certain parameter Vs, and Vs, the smaller Vs, the sharper will be this transition. So, but if you assume a very small, too much smaller value for Vs, this means that this formulation becomes exactly equal to the Coulomb's theory, to the Coulomb's theory, so the equal to the sign. Okay, so Vs generally can be assumed as 0.0075 meter per second. This is actually a velocity value. Okay, so let's see what happens. We go back to Excel. So let's say F isolation 2, always in terms of kilonewtons. So we get actually the friction coefficient times structural weight times the hyperbolic tangent of velocity value divided by Vs, and I will put Vs here. Okay, so let's add a new line. So this is Vs, and let's set this number. Okay, so here obviously we have already the maximum force because we start from maximum velocity. But then, okay, I want to add the graph to this one. So let's go to the selection of data, displacement, and force. Okay. 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 So you see something better is obtained. Okay, there are no that much points here to be included also in the unloading and loading branches. So you see, if if I decrease this value, something like 0.001, you see, we get exactly the same modeling assumptions of the Coulomb's theory, okay? But if I want to increase points, I have to increase also Vs value. So something like this, you see, there are some additional points, and then the maximum one could be this one, but there are a number of them. But actually, the best value is this one, just because this can be done, this model can be used to time integrate ground motions. So the a seismic response of a single degree of freedom oscillator, generally of oscillators, also lumped masses with multiple degrees of freedom. And this is actually, this provides a lot of additional points simply because we don't achieve the maximum velocity every time, at every time instant, and at every harmonic waves that we have during the earthquake. So this is still the best modeling aspect that we can catch for this particular assumption. But this is a strategy for the frictional response. We can do exactly the same of what generally SAP 2000 does within the definition of the software. So to model the frictional response through an elastoplastic behavior. So let's try to define these, the overall rule. Okay, so let's assume this behavior, and then we will try to model them. Okay, now we have almost finished with the theory. So So elastoplastic rule. I will give you a very fast rule to be implemented, which is very easy within actually also explicit method for time integration. So the ones that we are going to use. So what we are going to consider is something like this. Let's assume the general behavior. So this means that we can consider also hardening. Okay, because generally this rule will be applied can be applied both to the frictional response in order to actually model the frictional behavior, but then it could be also associated to lead rubber bearings, or can be directly be associated to curved surface sliders, where the post-yielding stiffness is directly the recentering stiffness provided by these spherical shapes of the sliding surfaces. So here we will have K2, and this is K1. Then we have the yielding displacement and the yielding force. I think that this is enough to describe, to fully describe these the overall behavior. So what happens is that generally we are able to define the elastoplastic rule according to the time step that we are going that we are considering, and with respect to the previous one. Okay, because the definition of this rule is something incremental. So we have to consider the previous time step and then to consider an incremental of force. So a variation, an additional variation of force, and then to check where we fall within the force displacement loop. So this is again F isolation and displacement. So I will try to better describe graphically this behavior. So generally, if we consider these, we can have these loops. So we have initial stiffness, then we have the yielding point, and then the post-elastic stiffness. Okay. And then we have the same also in the negative direction. Okay. And we have the connection, so the loading and unloading branches. Okay. So what happens when we time integrate the single degree of freedom? Maybe we are here. Let's say, let's start from 0. So at the beginning. So the main reasoning is that we can try to add the force increment with respect to the initial stiffness. So the first assumption is to get the second, the numerical value of the isolation force at the ith time instant as the previous one plus this increment, which is equal to K1 times variation of displacement. Okay, and then I check where my new point falls. Okay, which means if this is actually what the checks that we have to perform. If the new point falls within these two lines, so let's say the post-yielding lines, so this one and this one, so if this is true, actually the force that I've just computed according to that force increment is actually the correct value. Okay, because maybe I'm in an unloading rather than a loading branch. Okay, So K1 times variation of displacement is the final value of force at that time instant. Otherwise, if this is not true, maybe I'm either on this line or this line, which means that if I'm here, I just change color for you to better understand. Maybe then I'm here. I'm still on a loading branch, the initial one, okay? And then I add these, the first computation is to add the variation of force, and then I obtain these, okay? Okay, so I will check then, does my point falls within the post-yielding lines? No, at this stage. So this initial guess of the isolation force is wrong because I'm outside with respect to this theoretic cycle, and what I have to do is just to stop here. So I will compute actually the force response according to the proper yielding line. Okay, so this is just you just compute a trial for the force by adding this force increment, and then you check you fall within these two lines. That is the force, correct? And then otherwise you have to compute the proper post-yielding force according to one of these two lines. The way to select one of these two is just the direction of motion, which means that if the velocity value is positive, which means that you are going in that direction, you are loading the device, so you will consider this line, okay? If you are moving, I mean, leftward, this means that the velocity is negative, so you are moving in that way, so you are unloading the overall device, so this is the line that we have to consider, okay? So this strongly depends on the velocity at each time step, okay? And finally, this is the most complicated, let's say, hysteretic loop, hysteretic rule that we can consider. Then this can be applied to both to curved surface sliders rather than to lateral bed bearings. So let's summarize everything that we have seen up to now for modeling. Analytical modeling, I mean, for the isolation force. So rubber bearings can be modeled just in a single way. I mean, there are two ways. Just isolators. So the F isolation is equal to K times relative displacement plus damping coefficient times relative velocity, okay? Then we have the opportunity also to model everything. So isolators and flat sliders. So we will have to, again, to consider the same quantities, K times U plus C times relative velocity, and then plus the friction coefficient of flat sliders times the summation of all the vertical loads applied to, let's say, J. Applied to the flat sliders, they can be computed as an average value, as we have seen for the initial stiffness also yesterday in sub 2000, times maybe the hyperbolic tangent of relative velocity over Vs, rather than to use also the generally the elastoplastic behavior for friction. Then we have lead rubber bearings. And you have just one choice, which is elastoplastic. With hardening. And so we have actually the F isolation, which is a function of the stiffness, initial stiffness, post-yield stiffness, yielding displacement, and yielding force. Okay. And we have also to keep in mind that we have to define everything with respect to the previous step, and particularly with respect to the force value of the previous step. Regarding the curved surface sliders, we have two ways. F isolation is equal to, we have just the stiffness, which is W divided by R equivalent times the displacement, which is the recentering contribution, the linear one, plus friction coefficient, vertical weight times the hyperbolic tangent of velocity divided by Vs, rather than F isolation as elastoplastic, so function of K1, which is actually what we call the K rigid in sub 2000 modeling. And then we have K2, which is actually W divided by R equivalent. The dy is actually D rigid, which we defined yesterday. And the yielding force is equal to the frictional force. So this is equal to friction coefficient times the vertical weight. So this is elastoplastic. With hardening. Okay, so these are the main rules to actually to time integrate the single degree of freedom oscillator. Now we are going to do some numerical simulations within Matlab. And obviously, if you remember in the very first slides, when we when we discussed about the time integration method, you see that here in the second member of the first equation for the computation of the velocity, we have the application of the explicit method. So F isolation has to be considered at the height minus 1 time step. Okay, so this means that all these expressions should be considered at the height minus 1 for the computation of displacements. And once you have displacements, then you can compute also force, the force value of the isolation system at the height time step. So the general rule is to firstly compute the displacement response, because everything is referred to the previous time step, and then to update also the force response according to these rules. Okay. I hope everything is clear, but I think that it will be clearer for sure if we carry out some examples within Matlab. So let's start by considering some simulations, and we will consider actually the selection of seismic events that we considered yesterday. So this selection. Okay. So let's create a new script. and we call it stuff integration V1. And then we will try to obtain some functions for this theoretical response. So we want to, again, to load all the records. So let's start by one. So we compute the list as by analyzing the director. All the txt files which end with records, so that just records are selected and no spectra. And let's start with the first file. So that they were txt files, so we had to use actually import data in order to actually load the file. And then it was a 2-column file, so the time vector is the first column. And the second column is actually the ground motion time series. Okay, so let's check if everything works. Okay, so this is the first ground motion. Okay, and they were already values in meter per square second, so everything is okay. So let's start with the curved surface slider, which is the easiest one, because we have to define the friction coefficient equal to 5%, and then the equivalent radius of curvature, which is equal to 3.16. Then I want to show some particular strategies for that. So VS equal to 0.0075. And I think that's it for curved surface sliders. Okay. So let's define the displacement and the velocity responses as zero vectors. So U is equal to zeros. This is just to make the program to go faster. So 1 over length of t. And then the same for the velocity. Okay. Then let's also consider another vector, which is actually the vector for the isolation force. Okay. So let's consider all the time instances starting from 2, because we have 0 initial conditions. So for I, which goes from 2 to the length of t. Here we have just to write the integration equations. So what they mean is these two. Okay. So we have relative velocity at the height equal to the relative velocity at the height minus 1 plus, okay, we are missing the mass equal to the total mass times 9.81. Okay, then we have the mass divided by, okay, the sampling frequency is constant, but we can also say the time vector at the height minus the time vector at the height minus 1 times, okay, minus m times, this is W, and the mass is equal to, so we can say this one. So because this is a value on kilonewton, and then we need also the mass value. So mass times the ground motion at the height, as we have seen, then minus, this is important, otherwise we get something similar to what we obtained on Tuesday, F isolation related to the height minus 1. And that's it. Then we have the same for displacement. And then this one. Okay, here I think that I have to switch these. Okay, now it's right. Okay, now I have to update, once the displacement is computed and also the velocity, I can update the force response. So F isolation at the height is equal to, so for curved surface sliders, we can have these two strategies. Let's start from the first because this is very simple, okay? So we have W divided by R equivalent times the displacement at the height, which has been already computed here, and then plus friction coefficient times the weight times hyperbolic tangent of the velocity at the height, which is computed here, divided by Vs. Okay. So if we do like this, I mean, this is just a strategy to create a specific variable for the isolation force. This is better because this force is used for the time integration, and then directly the force used within the time integration method can be also drawn in terms of force displacement loop at the end of the script. Okay, so this is very important. Okay, let's comment this because we don't want to see anymore the ground motion, but we are interested in seeing the force displacement hysteresis. So U and force isolation. Let's check if everything works. Okay, so this is the result. You see that approximately less than 1 second just for the ground motion integration. And this is something very similar to what we obtained yesterday. I think that this numerical value was quite close to what we assumed yesterday, what we obtained yesterday. And you see the shape is the proper one, which is actually returned by the, we have the post-yield stiffness, which is the recentering one, and then we have the hysteresis related to the friction. So what we had is also this behavior, you see. This is the only, the only issue related to the hyperbolic tangent. So maybe we can see this issue better if we plot just the displacement signal. Yes. So you see, this is exactly the shape that we got yesterday. And you see that here we achieve some sort of residual displacement, but then it starts going towards zero. Zero is here. Maybe it's better grid on. Okay, yes. So you see that the overall system starts going towards zero displacement, okay, during time. But generally, this could be addressed to some behaviors. The first behavior could be associated to effective vibrations that we have simply because the ground motion is represented by significant values also at the end of the event, but this is unlikely to occur, okay? So maybe it can be just addressed to the definition of the force response, which means that you see in this drawing, this is the modeling that we have assumed, the hyperbolic tangent. So this means that for zero velocity, we have actually zero frictional force. So this means that the velocity at the end of a seismic event starts fluctuating around zero. So there is actually approximately zero frictional force, and what we have is just the recentering capability. So if we consider just zero frictional force, what we get is actually something which tries to slightly recenter the overall system very smoothly. And maybe this is not occurring in reality. So maybe, or maybe not, I mean, but there is the opportunity also to check if this could be, I mean, a residual displacement rather than we have effectively this behavior which goes towards zero, okay? And generally, residual displacements cannot be fairly modeled through the hyperbolic tangent, okay? Mainly because this issue, because there is a zero value of force for very low velocity values. And so whenever you have a zero friction, actually what you get is just the isolation response directly equal to the recentering capability. And the recentering capability, it is just a function of the displacement at that time instant. So this means that the system is forced to go towards zero. So maybe it is better to try to model the elastoplastic hardening rule according to this definition. So let's try to do this. Let's comment this. And as we have seen, we have to guess initially the force. So we need also an additional dummy variable, which is the isolation force. Let's call it F isolation D, which stands for dummy. And this is generally for programming issues, we can need some dummy variable to define the overall behaviors. So this is the case. And so let's check if what we have to model, we just write here all the parameters. So we need the K1 and the K2, so that then we can change these parameters according to actually lead rubber bearings, for instance. So K1 is equal to the rigid, the K rigid. So it was equal to friction coefficient times the weight divided by D rigid. Okay, and D rigid is equal to 0.0015, as we have seen yesterday. And then we have K2, and K2 is equal to W, so the weight divided by the equivalent radius of curvature. Then we have dy, which is D rigid, and then Fy equal to the frictional force. So the friction coefficient times the applied vertical load, which is actually the weight of everything we have above the isolation layers. Okay, so we have all the mechanical properties of the isolation system. And then now we can start by, okay, you see here, these equations are always the same because there is a F isolation. What changes from one isolation system to another one is the definition of the isolation force. That's it. So let's guess let's compute the initial guess of the force, so the dummy variable. So the F isolation dummy at the height is equal to, this is important, this is to be honest, generally a mistake that I currently do, but in this case, I try to remember it. The dummy force at the height is equal to the real force, so F isolation. And generally, what I'm wrong is when I'm wrong in this definition is that here I again type dummy variable, but this is not true. the dummy one is equal to the previous real force time plus the increment. So this I minus 1 plus K1, which multiplies the displacement increment. So U at the height minus U at the height minus 1. Okay, so then we have to check if let's go back to here. If the new point, the dummy force, falls within these two lines, okay? And the equation, actually, I just want to write it here. The equation slightly directly depends on the sign of the velocity. Okay, when the sign is when the velocity is higher than 0, we have this line. Rather than less than 0, we have this one. Okay, so I mean, let's assume that the equation is this one, equal to the sign of velocity times Fy plus K2, which multiplies the displacement minus the yielding displacement, which multiplies the sign again of the velocity. Okay, these two multiplications by the sign of velocity allows us to switch from this yielding point to this one. Okay, because when the velocity is negative, we have both the yielding force and the yielding displacement negative, so this becomes plus. When the velocity is positive, so accordingly we have actually the I mean the opposite, so positive value of yielding force and positive value of yielding displacement. And we can also say that okay, let's check firstly the position of the point. This will be very useful afterwards. So if this force is higher than or equal to the lower line, so minus Fy plus K2 times U at the height minus, I mean plus dy, okay? And the same force is lower than or equal to the same, but with by changing symbols. So this is a minus and this is a plus. So if it falls within the two lines, this means that the force, the real force, is the dummy one. So we have F isolation at the height is equal to the dummy one, which is not this one, F isolation dummy at the height. Okay. If it is not true, actually we get the real force equal to, let's consider this one, and then we have just 2 times sign of the velocity, and also here the one that we have written before. And okay, so let's check. Yeah, there is I think that the overall maximum displacement is approximately the same, it looks like. Let's check. Yeah, very similar. It is quite more similar to what we got yesterday in SAP 2000. So it was 113. Now I remember the numerical value. The shape is approximately the same as before. And let's check also the time series of displacement and the grid. Yeah, there still be some recentering again behavior. You see that there are also these fluctuations, and this is mainly because we have the elastic branch, okay, because we are using an elastoplastic behavior with the hardening ruled by the recentering behavior. But then you see that there is actually an asymptotic value for the residual displacement, and this maybe is not captured if you use the hyperbolic tangent. The best would be to use both of them and then to compare them. Let's try to do this. If we do like this. Okay. So I have just to call it 2, 2. I will surely go wrong in this, but let's try. Okay. Okay, and then this is 2. This is 2. This is 2. Let's try. Undefined. So yeah, we have to define them. Two. Okay. So let's try to consider these. Okay, hold all. And then the same here. 2 and 2. Yeah, there are some differences in the maximum value. You see that I remember that the hyperbolic tangent leads to a higher value for the maximum. You see 123 millimeters rather than 113 millimeters for the elastoplastic behavior. Obviously, when we use the elastoplastic, you see that there is an inclined unloading branch with respect to the approximately vertical one for the hyperbolic tangent. Let's consider also the shape of the displacement. So hold all and then plot U2. They are sampled exactly in the same way, so should work. Yeah, you see that we achieve a larger displacement with the hyperbolic tangent. The overall trend is captured, but actually there is this behavior which goes towards 0 with no actual constant value of residual displacements, even though actually they can be addressed to the same. So let's try to do the same comparison with respect to another ground motion, for instance, the second one. Yeah, in this case, they are pretty close, one to each other. And let's see also the time series for displacements. Yeah, this is a better result. So both the typologies are quite similar for results. And if we consider actually these, you see that the frictional response, I mean, the frictional force is exactly the same among between the two strategies, and also the inclination of the recentering behavior. So I think this is done for the curve surface sliders. Just to have a look at these, let's try to time integrate all the records, and so to store also the maximum displacement, just to have a look at this, equal to the maximum value of the absolute value of displacement time series. And then we consider, okay, for 1 to 7. Let's see if it works. Should. Okay, so you see at least maximum 1 second, we have done all the time integrations for all the earthquakes. We see here the last event is expected to cause a very large displacement for 40 centimeters. Okay, and then we have something smaller, quite smaller. Okay, higher. Let's check the bar plot. So the bar plot of the maximum displacement. So you see this is the 7th event leads to a very higher value of displacement. So maybe the mean response will lead to something similar, something higher than. Let's compute the mean of the maximum. Okay, so 185 millimeters. And if you remember, the design value was actually 180 millimeters. So approximately equal. There are just 5 millimeters higher, but there are also some additional, additional capacities of displacement according to the technology used for the realization of such devices. So 5 millimeters is okay. So we get exactly the right mean response. And this is mainly because the selection of seismic events is according to the spectrum compatibility. And so, yeah, maybe we get this behavior. So this means that the average is actually spectrum compatible with respect to the target spectrum, but the difference, the single event difference, is significant, as you can see. So this can be also is also expected for all the other isolation systems. So this is for the for curved surface sliders. Let's write it here. Curved surface sliders, and then we save, and we save as for. Let's start from the lead rubber bearings. Okay, and then we have just to modify. Okay, we don't need again the hyperbolic tangent, maybe. Or we can use it just to model also flat sliders. Okay, simply because if you remember, lead rubber bearings were just 4 over 24 supporting points of the overall building. So maybe it is better to also model that. So this is to model the isolation force just related to lead rubber bearings. And then we can also try to model the characteristics for fast sliders. I will have to change some properties. These, okay, let's erase these just because we need pure friction. Then we consider just 1% for the flat slider. Then we have the mass, the weight, okay. We have actually the number of flat slider equal to 20. Okay, so the W value for the flat sliders is equal to the W divided by 24 times the number of flat sliders. So this is just an average value for the applied vertical force to all the flat sliders, and then we have to modify these. Okay, so the all the quantities for the lead rubber bearings. So we have the yielding displacement, which is this number. So, okay, we don't need the rigid. We need, okay, this one, which is just a number, okay. Then the yielding force is here. Okay, then we have to multiply times the number of isolation devices, and then we have K1, and okay, which is this one. And then K2, which is this one. Okay. So I think that we can maybe an isolation, we can set the isolation number equal to 4 here, and then to multiply these times an isolation times an isolation, and then times an isolation. Okay, so let's also consider the force response for the flat slider, which is just this one. Friction coefficient times the weight for just flat sliders, and that's it. And so we need also the VS value. We have that, okay. And then, okay, but then we have also to remove here F flat sliders at the height of -1, and here we have to change flat sliders. Okay, should work. We don't have any more U2F isolation. Okay, that's it. Let's see what happens. Where we have to define it. Okay. Okay, flat slider. Okay, so you see, this is this is just the plot showing the response of lead rubber bearings. Okay, this is just for lead rubber bearings, and we have exactly the same design displacement as for the curved surface sliders, because we assumed the same design period and the same equivalent viscous damping. If we go to the bar plot, again, you see that we have the largest one, which is provided by event 7, and then the mean, you see, is slightly lower than the initial one, I mean, than the design one, but it is very, very close to it. It is, I think it is lower in comparison to the one returned by the curved surface slider. Okay, the overall behavior is different, but generally this is simply because we are also implementing the flat sliders. And the flat sliders just provide a very low additional force response, but with a little bit of hysteresis. So there is a slight increment of the dissipative capacity of the overall system in comparison to what we have assumed in design. So in design, as you remember, we just consider isolation devices, and we neglect actually the influence of flat sliders. We don't want to take care of it at the beginning. And then when we have to compute the assessment, we also model those devices. And this is maybe the reason why we obtain a lower value of displacement, but very close, lower, because we are actually increasing the dissipative capacity of the overall system by adding also the hysteresis response of the flat sliders. But it is very close to the design value simply because we have assumed 1% of friction coefficient, so the influence is very limited. So finally, we can we can also compute the same for rubber bearings, which is the easiest, the easiest case. So let's again save as, and we go to the third version of the file. So rubber bearings. And this is significantly simpler, just because we need the friction. Okay, we still have the flat sliders, so we just keep these updated. So the flat sliders are not 20 here, but they are 16. We just keep 1%. The mass is always the same. 24 is okay, the total number. Then the number of isolators is equal to 8. And so we just need K equal to an isolation times the single device stiffness, which is this one. Okay. And okay, we have to define C, and it has to be defined. It has to be defined according to the damping ratio 0.07 and the isolation period, which was actually this number. Okay, so we have omega isolation, which is 2 times pi divided by T isolation, and we have C, which is 2 times damping ratio times omega isolation times the mass. Okay. Okay, there is no hysteresis here, so we just need F isolation at the height equal to the stiffness times the displacement at the height plus C times the velocity at the height. Okay, so we don't need these. I think we are done with these. Let's check. Okay, you see that there is the common behavior for rubber bearings. So we have an elastic behavior with a very small hysteresis, which is returned by the constant value for damping ratio for all the events. Okay, this was actually very similar to what we obtained yesterday. And let's check the maximum displacement. The design maximum displacement for rubber bearings. It was, I think, very high. It was when I find 310 millimeters, so 0.31 meters. So let's check the bar plot for the maximum displacements. Okay, so we have something like this. So maybe we are about here, something less than 300 millimeters. Let's check. Mean, yeah, 274 millimeters. So a little bit lower. So this is actually good for us if we design isolation devices which have actually the displacement capacity which is higher than what we obtain from the assessment. This is good. It could be worse if we get exactly the opposite. So and again we have this difference which is lower than the design value of displacement, simply because again here we have the flat sliders, so we are increasing the dissipative capacity. And actually here the influence is much higher in comparison to the lead rubber bearing case, just because the rubber bearings, so the isolation system has a very low damping ratio for design. So this means that also the damping ratio, the viscous, the equivalent viscous damping associated to the hysteresis provided by flat sliders is small, but maybe it is more comparable into the damping ratio of the isolators in this case rather than in the case of lateral bearings. So the influence with respect to the additional dissipation capacity of the devices is much higher in comparison to the previous case. So I think we are done for this. And actually, what we want to do tomorrow is to compare not only the peak values of displacements, but we will also compare the whole time series of displacement, because what I want you to see is that these computations for the single degree of freedom integration, if we are able actually to model the proper hysteresis rule, actually returns a very good estimate also for the whole duration of the ground motion. And this is mainly, this is a confirmation for what we have seen last week for the main assumption of the base isolated structures considered as a single degree of freedom oscillator. And even though yesterday we have developed a full three-dimensional finite element model of our structure, you will see that there is that the final results will be much comparable, pretty much comparable with respect to other simulations for non-isolated structures, I mean. And for sure, these I've just shown these rules for these applications, I mean, for isolated systems. But these are generally, these can be generally used for any kind of systems. For instance, the elastoplastic with hardening hysteretic loop can be adopted for generally any kind of applications whenever you need the definition of a yielding point and a post-elastic, a post-yielding stiffness. And also the frictional response can be also used for frictional dampers and so on. So these are useful for any kind of application whenever you have to model such a typology of hysteresis, I mean. So I think that this is it for this lecture. Is there any question about this? Okay, yes, I will provide the scripts so that you can go back to all the details and see how we have modeled this if you were not able to follow all the computations. And I think tomorrow we will be able also to check the comparison between these results and the results returned by the analysis of all the models that we have developed yesterday. And as I mentioned at the beginning of this lecture, I will provide by email within today a very easy homework to be solved within next Tuesday, which will deal with the design of isolation systems for a very easy example. So I think this is it. Thank you all, and have a nice day, and see you tomorrow for the last lecture of this short course. Goodbye, guys.
Thank you, Professor. Bye.
Bye.